Hello all, welcome to this course on time series modeling and forecasting using R. Now again we are mid of this week and then the focus area that we are discussing this week is all about multivariate time series analysis, right. So if you vaguely remember in the last couple of sessions we sort of introduced the idea of why do we want to transition from a univariate time series process to something called as, let's say, either bivariate or multivariate time series analysis, right. And then even the last lecture, if you don't remember, then what exactly do you mean by a multivariate time series process, then probably I'll very quickly revise that and then we'll sort of move on from there. Okay. Now again, the whole idea of explaining multivariate time series analysis to somebody is not really easy, right. So my strong suggestion is again that you should again go back and then try seeing some of the initial videos in this week and then sort of repeat viewing of those sessions, right. Just to sort of understand that if you're transitioning from a univariate YT to a notation which is multivariate YT, then what differences do you have to take care of, okay. So for example, what do I mean by that statement is that initially up to now we have discussed that, let's say, YT is a time series process, and then one particular realization of YT could be something like, let's say, Y1, Y2 up to Yn, right. So let's say you take an example of any univariate time series example. So let's say temperature data or stock price for a single stock and so on and so forth, right. So let's say YT denotes the temperatures. Let's say YT denotes the monthly temperatures for a year. So all these would be the monthly temperature values which are realized, or Y1, Y2 up to Yn is nothing but the collected data, right. So this is an example of a univariate time series. But the moment you transition from univariate to multivariate, now let's say the notation changes very slightly, something like YT inside curly brackets, and then now YT becomes a collection of random vectors, okay. Even here YT, when you talk about a univariate situation, YT is a single random vector, but now when you talk about YT is a collection of several random vectors. So let's say I can write down something like Y1 and then Y2 up to let's say K, okay. So my YT, which is a multivariate time series process now, is a collection of a k dimensional random vector. So Y1, Y2, Yk in themselves are nothing but individual time series or individual univariate time series, okay. And again, properties of any multivariate time series process like YT, then interconnections between any two vectors here, so let's say Y1, Y2, right. So all these properties have to be carefully defined. And hence we have a notion called as, let's say, cross covariance. So in the last lecture, if you remember, we discussed an idea about cross covariance. So cross covariance means nothing but the interrelationship between any two series of the same collection of random vectors, which is YT. Alright. Okay. So now the slide that you see in front of you discusses some results on a technique called as linear filtering. Alright. Now we'll quickly try to understand as to what do you mean by, let's say, filtering, and then what do you mean by linear filtering, and what all are the ingredients that go inside a filtering, okay. So now let's say that you have xt, which is a r dimensional input series. So xt denotes the input series, and let yt be a k dimensional output series, okay. So assume that you have some input variables and then you have some time series model or time series structure which sort of outputs a output series. So xt is a collection of r such random vectors, which is the input series, and similarly yt is a collection of k such random vectors, which is called as the output series. Then how can we define a multivariate linear, also called as time invariant filter, relating xt and yt? So in other words, how do we sort of define some relationship between this input series xt and the output series yt, okay? And this is exactly that equation. So let's say yt equals some infinite sum j going from minus infinity to infinity, and then collection of some coefficients, let's say psi j, and then applied on xt minus j. So again, just to reiterate, so xt is the input series, yt is the output series, and through this equation we are sort of creating that multivariate linear filter, okay. So in other words, such an expression is called as a filter, and why filter is a technical term in time series which denotes the fact that the interdependency between an input series and the output series, okay. And again, since we are dealing with a multivariate sort of a structure, then all the psi j's are themselves some matrices. So let's say k cross r matrices. And why K cross R? Because both these input and output series are R dimensional and K dimensional respectively. Okay. So, this is a definition, or this is the expression of a particular multivariate linear filter. Now, again, what would happen if psi j is 0 for all indices which are negative, or for all j which is less than 0. Okay. Now, again, just for a second, if you go back to the slide which we saw earlier, now again remember that the summation is running from minus infinity to infinity. Okay. And now on the next slide, we are sort of assuming that all the negative indices, so in other words j being less than 0, then the corresponding value of psi j is 0. So, in that case what would happen is that the summation would be sort of narrowed down to only positive terms. So, j would be running from 0 to infinity, but the structure remains the same. So, yt equals summation j going from 0 to infinity psi j and then xt minus j. And in this situation, the filter is physically realizable or causal. So, again these are some technical terms we sort of put forward to the filter. Okay. So, in this case we call that the filter is physically realizable or causal. And in this case yt is expressible only in terms of present or past values of the input series xt. And naturally so, right. So, if the summation is only running from 0 to infinity, so let us say what would happen if you put 0, so value of j to be 0, this becomes xt, right. Then if you put value of j to be 1, this becomes xt minus 1, then xt minus 2 and so on, isn't it. So, essentially the values which yt depends on are nothing but either the current value of xt or its past values, but not the future values. Okay. So, this is the statement that we have here. So, in this case yt is expressible only in terms of present and past values of the input series xt. Okay. Now, another definition we will put forward is when can we say that a linear filter is stable. So, you have a understanding or a notion of a filter being stable. Okay. So, for that we require another ingredient called as a norm. So, let this notation, right, denote the norm of any matrix A, which is defined as nothing but norm of A is nothing but trace of A transpose A. Now, here assume that A is a matrix, right. So, this is the notation for norm of A, and then the actual expression is norm of A is nothing but trace of A transpose multiplied by A. So, under this condition, so if summation j going from 0 to infinity norm of psi j is finite, then we say that the underlying linear filter, which is given by this expression, is stable. Okay. So, this is just a small definition of when do we say that a linear filter is stable, whenever this condition is satisfied. Okay. Now, again I am pretty sure that all the notations are slightly difficult as compared to earlier sessions, let us say when we deal with only univariate situations, because naturally so. So, if you are transitioning from a univariate to let us say even bivariate or let us say multivariate, then you have to have some understanding about the dependencies between let us say matrix multiplications or idea of inverse, adjoint, which we will soon see of course, right. But then you have to sort of have some basic idea about matrix theory or linear algebra. Okay. Okay. So, now if the linear filter is stable and the input random vectors xt have finite second moments. Okay. So, if the linear filter is stable, in the last slide we saw when do we say that a linear filter is stable, and on top of that if the input random vectors xt have finite second moments, then for the output vector yt the filtering representation exists uniquely and converges in its mean square. What do you mean by that? So, converging in mean square means if you take the expectation of yt minus whatever you have on the right hand side and then the same thing and the transpose of that. So, this should approach 0 as n tends to infinity, right. So, under this condition which is given by star, we will say that the filtering representation exists uniquely and it also converges in mean square. Okay. And now on top of that we can define let us say the covariance matrices or the correlation matrices and so on and so forth. Okay. So, if the linear filter is stable and xt is stationary with cross covariances denoted by let us say gamma xl, then it also means that yt is also stationary with cross covariances given by this formula. So, gamma yl is nothing but covariance between yt and yt plus l. Now, again there is nothing new here because this is just the definition of cross covariance. and then the expression for that is given by this structure. So here you have two summations running from minus infinity to infinity, and then the psi I coefficients, then the gamma variable in terms of x. So this expression that you see in between is nothing but the cross covariance for the random vector xt, isn't it? So the subscript x denotes anything related to xt, subscript y denotes anything related to yt. Okay. So this is a not that easy structure, I'll say, but then nevertheless it sort of defines the cross covariances among the random vectors comprising of yt. Okay. So these are just some results on linear filtering. So let's say, for example, when can we say that the filter is existing uniquely, or when do you say that the filter sort of converges in mean square, right? And further, how do you find out, let's say, the covariance matrix or the cross covariances, and so on and so forth. Okay. Alright, so now we will slowly transition on a slightly different trajectory by defining some models. So now that we have some understanding about what you mean by, let's say, multivariate time series structure and so on and so forth, so now is the correct time to sort of define or put forward some multivariate time series processes. Okay. So the first representation is given by Wald, and then hence the name is Wald or MA representation of the series, right? And here again it will be a good idea if you again go back to the MA session from the univariate structure, and then just sort of understand that how a MA process looks like, right? Now again, just to give you a very quick refresher, MA process is nothing but you have the time series yt on one side and the moving average in terms of all the random errors on the right hand side. Okay. So similarly here something of a similar nature should happen. So even if you transition from a univariate MA to, let's say, multivariate MA, things won't change very drastically. Okay. So what exactly do you mean by this Wald representation? This is in fact also called as an infinite MA representation of a stationary vector process. Okay. And why infinite, we will soon see. Now again, let's assume that yt is a multivariate stationary process. So again, yt as before is a collection of some random vectors with, let's say, mean vector mu. So yt is a k dimensional collection of random vectors. So yt is k cross 1, and similarly the mean vector has to be k cross 1. Okay. Then this process, so yt minus its mean vector equal to an infinite sum. So j going from 0 to infinity, psi j et minus j is given by nothing but the Wald representation or the infinite MA representation of the series. Okay. Now, a couple of things here. So firstly, why infinite? So infinite because you have an infinite sum, right? And the second question is why MA? So why MA? Because if you, let's say, if you take this mu on the right hand side, then this is nothing but the MA structure, isn't it? So you have yt on one side and nothing but the moving average or collection of some random errors on the other side, which is nothing but the MA representation. Make sense? So this is exactly what we will do now. So we will sort of transport the mu on the right hand side, and then yt is nothing but mu plus the infinite sum, where of course what is psi b? So psi b is nothing but summation psi j b to the power j. So this psi b is nothing but a k cross k matrix of backward shift operators, right? So again, remember this capital B denotes the backward shift operator. So again, remember this capital B denotes the backward shift operator, right? And then if you are representing in a multivariate sort of a structure, then you should have a matrix. So k cross k matrix of backward shift operators. Okay. Alright, so now the next model we will discuss is a more generalized version, which is called as vector autoregressive moving average, right? Or in short, we will call that as a VARMA model. So VARMA. Okay. So again, VARMA should kind of have a similar structure as a univariate ARMA process, isn't it? The only difference is there will be some matrices there, there will be some random vectors there, and so on and so forth. Okay. So in general, a VARMA PQ process could be denoted by this expression. So you have psi PB or rather phi PB on the left hand side applied on yt minus mu equal to theta QB applied on the random errors, which is ET. Now remember one thing, so wherever you see ET, so all these ETs are not univariate, right? Because we have a multivariate structure. So all these ETs are assumed to be white noise multivariate processes. So white noise or rather multivariate white noise processes. In the last session, we sort of discussed what do you mean by a multivariate white noise structure. Okay. So all these random errors are no longer univariate, but they take a multivariate sort of a structure. Okay. But again, all the other things, if you notice in this slide, are sort of similar to when we discussed ARMA process in a univariate case, isn't it? Because again, this phi p b coefficient is nothing but phi 0 minus phi 1 b minus so on, and then phi p b to the power p, and similarly theta q b coefficient is nothing but the same thing. So theta 0 minus theta 1 b minus so on and so forth up to theta p and then b to the power p. Now here the only difference is all these coefficients, right? So phi 0, phi 1, phi p, or theta 0, theta 1, theta p. So these are some matrices, okay? And then these are not some single constant. So these are matrices now, okay? Alright, so some specialized cases, so what would happen if you plug in q to be 0? So if q to be 0, then the equation reduces to this form. So phi pb applied on yt minus mu happens to be only the multivariate white noise structure, which is ET, and this model is nothing but VAR with an order P, right. So you don't have any MA structure or you don't have any MA component here. Similarly, on the other hand, what would happen if P happens to be 0? So when P is 0, this implies that YT minus mu equal to theta QB coefficient applied on ET, and this process is nothing but VMA with an order of Q. Okay. So when we put forward an equation for Varma PQ process, which is general looking vector autoregressive moving average, then depending on the fact that whether my P could be 0 or Q could be 0, I can sort of reduce the models to be either VARP or VMAQ, right. Okay. So now further we will try to understand some properties about this VARMA process. Okay. So firstly, this process would be stationary if it can be represented as a convergent vector moving average process of infinite order. Now firstly, what do you mean by that? So again, this is the structure written in a slightly different way. So let's say yt equals mu plus et plus summation j going from 1 to infinity, and then some psi j coefficients applied on et minus j, right. Now again, just for a second, if you compare this equation to the equation that we had earlier, right. So the equation for the VARMA process is given by this, where you have a phi pb coefficient and then yt minus mu and then theta qb coefficient applied on et. Okay. Now just for a second, let me write down the same equation here, and then we'll try to match them. So phi pb, right, and then yt minus mu equals, let's say, some theta qb coefficient applied on et. All right. So this is the exact equation from the last slide. And then we want to sort of compare this equation and then this equation, isn't it? Because this is just another way of writing down the same VARMA equation. So here, if you notice, what we are doing is we are trying. So first thing is we are bringing this mu on the other side, right? The other thing is we are taking an inverse of this phi pb coefficient and then taking them on the RHS. So what would happen if you take this phi pb coefficient on the RHS? You have to take an inverse of that. Okay. So essentially yt is nothing but mu plus et plus again this infinite sum j going from 1 to infinity, and then psi j coefficients applied on et minus j. Now the whole thing is what is psi j, right? So whole thing is what is psi j, and then from discussing what is psi j, we will have some connection between these two equations. Okay. Or in other words, we can write down yt to be nothing but mu plus psi b coefficients applied on et, where the psi b coefficients are nothing but 1 plus the same summation j going from 1 to infinity psi j b to the power j, and then this expression is nothing but my phi b coefficient and then inverse of that into theta b coefficient. Okay. Now again, what exactly is happening here, I will maybe explain in a minute or so. So from this equation, can you see that yt minus mu can be written down as phi pb coefficient inverse, isn't it, and then theta b coefficient applied on et. Make sense? So I am simply taking the inverse of the matrix phi pb and then taking that on the right hand side. And now from this equation I can take mu on the other side. So yt happens to be mu plus my phi pb coefficient inverse of that, and then theta qb coefficient applied on et. Make sense so far? So this equation is essentially nothing but this expression that we are trying to simplify in the last line, isn't it? Because here yt is what? Yt is mu plus psi b et. So again, if you compare this equation and the first equation you have here, right? So essentially psi b should be nothing but equal to phi pb inverse into theta cube b, isn't it? Because this should match, right? So phi pb inverse theta cube b should be nothing but exactly equal to my psi b coefficient, which is nothing but what we are trying to explain here. So psi b eventually is nothing but equal to my phi b inverse into theta b. Okay. Now the whole point of sort of rewriting the initial equation into a different form is, the most important point here is that such a structure is stationary. Okay. So process is stationary, as stated here also, that process is stationary if it can be represented as a convergent vector moving average process of an infinite order. Now what extra thing is special about this structure is nothing but this is a infinite MA process. Can you see that? Because on the right hand side you don't have any YTs, right? So this is nothing but a combination of simply errors, isn't it? So this is nothing but a VMA process of an infinite order. So an infinite moving average process. So essentially, just to summarize this slide, is that when can we say that a V-ARMA process is stationary? If a V-ARMA structure can be represented or rewritten as a convergent vector moving average process, or in other words VMA process of an infinite order. Okay. So I guess this is just a rule of telling whether a V-ARMA process is stationary or not stationary, etc. Okay. Okay, so I think this slide is just a small refresher about, let's say, what do you mean by determinant or what do you mean by adjoint, right? So again, let's say A be a matrix whose determinant is denoted by determinant of A and the adjoint by adjoint of A. Then of course you must have studied back in, let's say, early college days when we took a course on linear algebra, that I can actually write down the inverse of the matrix as something like 1 by determinant into the adjoint. Okay. Now again, specifically I am suggesting that if you don't have any background about linear algebra or matrix theory, then probably pick up any basic book and then all these identities would be there. Okay. But using this relation, we can actually write down a small expression about the inverse of this phi z matrix. And why are we more concerned about the inverse of the phi z matrix? Because again, if you go back for a second, we have exactly this matrix with us, isn't it? So it will be a nice idea to sort of express this inverse matrix using, let's say, determinant or adjoint and so on. Okay. So I can write down the inverse of this phi z matrix as nothing but 1 by determinant. So I have determinant inverse into phi star z, where phi star z is nothing but the adjoint. Okay. Thus, if you again go back to the earlier slide, I can actually write down the V-ARMA equation in this form. So yt is mu plus determinant of phi b inverse into the adjoint, so phi star b, into the theta q b coefficient applied on Et. Alright. Now the only thing I am doing here is that I am expressing the expression on the last slide in the form of 1 by determinant into its adjoint kind of a form. Okay. And again, the whole idea is that the process is stationary if this guy, so determinant of psi z inverse, is convergent whenever absolute value of z is less than 1. So you have one more simpler looking idea as to when do you say if the process is stationary or not. So when you write down such an expression containing determinants or adjoints and so on and so forth, then the only thing you have to prove is that whether your 1 by determinant or determinant inverse is convergent for every value such that mod z is less than 1. Alright, so once you define a general V-ARMA process, then we can sort of pinpoint to some specialized processes. So the first one is, let's say, VMA of order Q. Okay, so this process is nothing but VMA of order Q, or vector moving average process of order Q. Okay, so here we can fix, so rather than fixing the upper limit to be infinity, we can fix it to be Q. Okay, and then again we'll again go back to the earlier equation, and then how can you write down that equation? So yt would be nothing but mu plus et plus summation j going from 1 to q theta j into et minus j, or I can write down this concise form. So mu plus theta b coefficients applied on et, where the theta b coefficients are nothing but given by that expression. So, you have an identity matrix of order k plus theta 1 b plus theta 2 b square and so on and so forth up to theta q b to the power q. So, this theta b coefficient that you see here is nothing but given by that expression. Okay. So, such a structure is called as VMA of an order q, or a vector moving average process of order q. Okay. So, similarly we can talk about some specialized examples. So, let us say vector MA1 process. So, this is VMA of order 1, right. Now, again just for without loss of generality we can assume that the mean is 0. So, again we can invoke some recursive substitution here. So, this is the equation for VMA1, isn't it. So, again if you are not very comfortable you can pause the video and then just check. So, this is my VMA1. So, yt equals et plus theta 1 et minus 1. Okay. Now, here what I can do is I can express or sort of re-express every time this et minus 1 as yt minus. So, from here what can I do? So, my et minus 1 is nothing but yt minus et and then sort of divided by theta 1, isn't it. So, what would happen if I go on sort of putting this expression every time here? So, the equation becomes et plus theta 1 yt minus 1 minus theta 1 et minus 2. And why is that? Because from this equation, right, from that equation, can you see that I can write down et as what? So, from this equation et becomes yt minus theta 1 et minus 1, isn't it? And then hence et minus 1 would be nothing but yt minus 1 minus theta 1, right, and then et minus 2. And then this I can replace back where I have et minus 1, right. And here I can sort of have a recursive substitution. So, the first stage would be that, right, and again I can replace back et minus 2 similarly and so on and so forth. Okay. So, eventually the expression would be nothing but that, which is theta 1 yt minus 1 plus theta 1 square yt minus 2 and so on and so forth up to et. And this expression if you see closely is nothing but the expression for a vector autoregressive process of an infinite order. Okay. So, this is nothing but VAR infinity. So, in short a VMA1 process can be written down analogously as a VAR infinity process. Okay. So, a vector autoregressive infinite process can be rewritten as a vector moving average process of order 1. And the last thing we will deal with in today's session is we can sort of get the autocovariance matrix of the process and so on. So, I can write down the autocovariance structure by this expression. So, gamma L equals expectation of yt plus L, and then again by taking some cases. So, let us say what would happen if L is 0, what happens if L is 1, or what happens if L exceeds 2 and so on and so forth. I can put forward some expressions for writing down the autocovariance structures of the VMA1 process. Okay. So, sigma plus theta 1 sigma theta 1 prime if L is 0, then sigma into theta 1 prime if L is 1, and then 0 if L is bigger than or equal to 2. Now, in the next session, it will be the last session which will be theoretical in this week. So, I will try to take up one example, and then towards the end of next session, we will also elaborate or sort of give you lots and lots of examples where you can sort of apply, let us say, either a Varma process or a VAR process or VMA process in a practical sort of a situation. All right. Thank you.